Hello. Yeah, thank you. I hope you are still alive after lunch. I am. I think my adrenaline level is pretty high, so I won't have any problem with keeping awake. Let me start with saying that I'm really super happy to be here. I've dreamed of being here in person since at least a decade. And now I'm not only here, but also can give a session. And then I would like to continue to first thank you, Mark, for giving the machine to me for this presentation, because as I was flying in from Germany, I would have had a hard time bringing a machine with me. And then I would thank Stefan, who is not only operating the pretty complex demo, but he has done significant contributions to the project, and we would not be here presenting this without his help. Okay, let's get started. So the Raspberry Pi Pico, I presume about everybody knows about this device right now. The first thing I think interesting is it's both a development board and it's a surface mountable module in the same thing. So this was one of the first aspects that make it pretty affordable. It consists primarily of an RP2040 MCU and 2 MB of SPI flash. The RP2040 MCU has two ARM0 cores. It has 264 kilobytes of RAM. It has no internal flash at all. So the external flash is obligatory. A little bit interesting is the bootloader, which works as a USB mass storage class device. So you just boot it into this mode and drag and drop any firmware on the device for flashing. This is great because if you have a device in the field, that is something that about every user is able to do. There's no problems in support like, I don't get the latest thing flashed, or I have bricked my device, or whatever. This is really foolproof. Everybody gets this done. Great stuff. And the most likely most interesting thing about this is the programmable I/O, short PIO. Okay, let's talk about the programmable I/O. If you have an MCU, it has usually peripherals built in, like UART ports or SPI interfaces. And these things are typically created from so-called macro blocks. And now the idea of PIO is that you take these things, these individual macro blocks, and provide the user of the device, the programmer, to do something on his own with these macro blocks instead of only having pre-configured peripherals. What these peripherals are supposed to do is not expressed by things like Verilog, but these things are expressed by state machines. And you have two PIO instances with 4 state machines each. And this thing is done with a custom assembly language that allows you to describe the state machines, what they are supposed to do. And each operation takes exactly 1 cycle. Let's have a look. This is a very small but not super, let's say, simple example. You're not supposed to understand every detail, but I thought you might be interested to have at least a little look. So what's going on here? This pull means that the PIO state machine is pulling a value from the ARM core into its output state register, output shift register, sorry. And then here, one of the very few variables are set to the value 7. And then there's a loop. And then one bit is taken from the output shift register and actually put out on the defined GPIO pin. And then, as long as X is not 0 or below, sorry, I don't know exactly, the thing continues. Interesting is what we have here. This is a side, which means you have a side effect or a side pin. This means here that another pin, which happens to be the same, is set to 1. But still, all this pulling something from the ARM core into the shift register and setting this pin to 1 is all done in 1 cycle. And then here, setting it to 0, again, done additionally, but in the same cycle. And now we have here those two 7s and the 6. This means wait for additional cycles. So this line here means basically, okay, get the value from the ARM core, put it into the output shift register, additionally set this thing pinny to 1, and then wait for another 7 cycles. So in general, 8 cycles passed. Here again, the actual operation, 7 cycles wasted, those they are 8. Here we have 2 operations, 1 cycle each, wait another 6, again 8. So you have 3 things, everything is exactly 8 cycles. By this way, you get very precise things, and you can implement low-level, high-speed protocols with exact timing requirements. This is the basic idea of this whole thing. Yes? So it was not super simple, but not super complex, just something for you to get a little feeling of it. Okay, now we have an idea of the RP2040 a little bit. Let's look on the other side. 6502. Its interface to the outside world is about read and write cycles. That's basically all it has. Write cycle means it puts an address on the address bus, waits a bit, then it puts the data on the data bus. Read cycle, putting address bus, waiting a little bit longer, and then sampling the data bus. It expects at this point that the data bus contains the data it should read in that read cycle. That's the story. So where's the challenge? If I want to have an MCU connected to the 6502, then I have a certain amount of time between I get the address on the address bus until I have to put the data on the data bus. I can only start this operation after the address is there, because otherwise I do not know what data is requested. So I have a pretty precise little time to do these things, and this is usually, traditionally, hard to do with an MCU. Even if you have MCUs with a frequency of several hundred megahertz, this is not easy. And the Raspberry Pi Pico can now use these PO instances to do this. And that means that you don't need additional logic as you had so far, typically things like CPLD logic or stuff like that. With the PO, you can manage this with combining the PO instance and either the ARM core or maybe a DMA channel. The obvious benefits are this is very cheap and it's very simple to create because you don't have any special chips that you need maybe a specific programmer hardware or whatever. You just have this thingy with a USB cable. You just drag and drop the file onto it. That's all there's to do. Good for doing it on production process, good for doing it in the field. And the last thing, I think everybody of you who has already written 6502 assembler could have a feeling what this PO code that I showed you does. If I would have shown you some Verilog code, then about everybody, but maybe one person in the room would not have had any idea what I'm talking about. And this is, I think, very nice, especially for retro computing things like what we are doing here, because it fits so nicely. You have this assembler on the 6502, you have the PO code on the RP24. These things fit nicely together, at least from my perspective. Okay, I was in the introduction, we heard that I want to talk about similarities and differences. So a little bit about similarities. The Pico-based cards I have looked at have several things in common, and I've written them here. Usually, when it comes to connecting an RP2040 to the 6502, you will need one of the two PO instances to do the low-level communication with these read and write cycles of the CPU. And then you will have one of the two ARM cores, and this ARM core is busy waiting on the address data to come in. Usually you don't use things like interrupts because of interrupt latency. You're really doing a busy poll. You're basically wasting one of your two ARM cores exclusively just on the purpose of communicating with the 6502. All the projects that I've looked at, including the one I've worked on, are working exactly this way. you don't want to have any interrupts on that ARM core. Then there's the other ARM core, and there you have different options. There are projects like when you do something like video output, you have, again, strict real-time requirements, and you fulfill them with these on the second ARM core, doing PO again, the second PO instance. Great, you have two of them. Or if you do other things like I/O with the USB port or driving an SD card, then you have, let's say, more like relaxed environments. Then you have your third-party libraries that do some interrupt processing and whatever, but you're not in a strict real-time environment anymore. So it's really like very nice that you can say one half of the RP2040 is a strict real-time environment, and the other half is like, more like, relaxed. Works pretty nicely. It's, I think, a nice environment really to work on. Okay. But it's not only about 6502, it's actually about Apple II peripheral cards. What do we have there as well? We have usually an Apple II peripheral card consists of some I/O device or several I/O devices and a ROM for the firmware dealing with those devices. And the 6502 uses memory mapped I/O, so both things are done in the same way. With other CPUs, that would be different. So if we say we want to have I/O and we want to have a ROM, everything is basically the same stuff. It's all about the 6502 cycles that you want to get working with your RP2040. So what are the specific challenges when it's coming to an Apple II peripheral card? First, the whole thing is about 5 volts, and the Apple II RP2040 is strictly 3.3 volts. It's not 5 volt tolerant like, for example, an ESP32. Therefore, you need some form of voltage level shifting. And the other thing is that the RP2040 has 30 GPIO pins. This is pretty much for today's applications where everything is about serial communication, but it's a little bit low or even too low when it comes to old-style parallel stuff. And additionally, the Pico board that I showed in the beginning uses 4 of those pins for internal purposes. These internal purposes are not interesting at all for the use case we are talking about here, so you can consider those 4 pins as wasted, which is not nice as you have so little at all in the first place. So now you have a good understanding about the environment such a project is living in, and then we can look at the different approaches, how they are taken by cards. One additional thing to think about is a peripheral card expansion ROM. It's a very specific thing. I think most of you will know, just a quick refresher. It's about the ROM between page C8 and CF. These pages are available to all peripheral cards in the machine. Of course, it can only be one active at a time. Therefore, there's a little protocol. That protocol says when the CFFF is accessed, every peripheral card has to turn off its ROM, and then the card where it's, let's say, slot ROM, the one on the C slot number, is accessed, then this is allowed to turn its ROM on again. You can do this either with an explicit access, like LDA, STA. Usually it's done as a side effect of executing code there, so the fetch cycles of the CPU will turn on the expansion ROM, usually. Okay, why is that interesting? It's interesting because, as I mentioned before, we need level shifting. The usual way to do level shifting is with transceivers. Transceivers need to be told in which direction they are supposed to work. And usually, you can drive the direction pin of your transceiver simply by the read-write pin of the 6502. Every time it wants to read, let's do it this way. Every time it wants to write, do it that way. But now we have the expansion ROM. So the 6502 comes along and says, OK, I want to read on, let's say, something like C8 whatever address. But I cannot just turn on my transceiver, because if I'm not the active card, I will cause bus contention and maybe even break something physically. So this is not going to work this way. So supporting expansion ROM in the presence of transceivers is a little additional complexity that needs to be solved. Yeah, you need to be aware of. So let's see. Now I'm getting to actual cards. I think the simplest one I came across is the A2 Pico. It simply does not support expansion ROM, so it does not have this issue. It uses 2 transceivers. They are driven by the 6502 read-write pin, very straightforward, everything pretty straightforward, because it only needs to decode 8 bits of address space. It gets along very nicely with these GPIO pins. There are even 4 GPIO pins left for a little SPI interface to drive an SD card. This card basically one-to-one follows ideas I have posted on a wiki I have created. I have just had the idea you could do it this way. I've never done it my own. Someone else did it. It works fine. I think this is one you've been waiting for all. Let's have a little bit more information on this. It's a video card, so it needs to have access to all the memory because it wants to read all the memory. It needs access to the full address space. So we have 16 address pins, we have 8 data pins, so it's a lot. So here we have multiplexing. These 24 pins are multiplexed to 8 GPIO pins on the RP2040. And this is done with having 3 distinct transceivers, which are this time controlled by the RP2040. And this is in general a great idea, but it takes away some time because these transceivers need to be driven by the RP2040 at the right time, and it needs to wait a little bit time until the transceivers have actually stabilized the data lines. So yeah, a nice idea, but yeah, take some time. If the time left for the ARM core is enough for your purpose, great, but it's not, yeah, it's reducing your possibilities on what you can do on the ARM core. That's, I think, important, at least to me. Some more details. I think there are some aspects I think it's a little bit strange about the card. The card, as a VGA output card, has no need to put any data on the data bus at all. It's only supposed to be an output thing. Nevertheless, it contains everything necessary to do so. And if you use an Apple II VGA card and actually try it out and you just read in its I/O addresses, you will see that it actually puts values there. On these 16 addresses, it will put the values from 0 to 15. So it does do it correctly. So everything is there to do it, both software side, firmware side, hardware side, also not necessary. There's even in the schematic, it says, oh, we could extend this to not only have those 16 I/O addresses, we could also have these 256 ROM addresses. So someone has had the idea of doing stuff with that thing, which is, but until today, not taken benefit of in any way. On the other hand, the project side says that it cannot sync the VGA signal because it does not make use of the sync pin in slot 7. I think it's a pity. I've not said it on my own, but given the site, because this shows that even the author considered this a pity. But it could have easily be solved by not doing this stuff, but instead doing that stuff. For some reason, the card has opportunities it doesn't make not use of, but it keeps other things it should do and doesn't do it. So I personally don't understand why it's done this way. Another way to move forward would be to go away from the Pico board and use the RPi 2040 as a bare thing, because then you have 4 more pins to work on. Okay, next card. This one is a variant or derivate of the Apple II VGA. This one does expansion ROM support, and this card actually has firmware that does stuff on the data bus. Because beside being an VGA card, you can as well configure it to emulate an AppleCard CPM card. In this scenario, it runs a Z80 emulation on the RP2040 core. Interestingly, this card does not do the additional stuff with the ROM encoding and protocol in the RP2040, what I consider would be straightforward. The guy doing this one decided to have a CPLD on the card doing this thing. From my perspective, this defeats the whole purpose, because if I have a CPLD on the card, as you will tell me, I'm true, you can have all the functionality easily implemented in the CPLD and be done. There's no need for a Pico in the first place. So combining a Pico with a CPLD is, from my perspective, basically the worst case. Combining worst things of all worlds. Nevertheless, it's there. People like it. Now coming to my card. This is something that Glenn has designed and I have been helping to work on. Basically the same model we have with the Ethernet and Ethernet 2. This card is in one aspect different. It does not use transceivers for level shifting. It uses bus switches for level shifting. Bus switches do not have a direction pin. Bus switches are, you can say, let's say, always bidirectional, simultaneously or bidirectional. There's just no idea of a direction. The perception of a direction is not present for a bus switch. Therefore, this allows us to do things like if there were no level shifting. And this allows us to say we can have the whole expansion ROM protocol implemented inside the RP2040 without additional effort. And we don't need to drive transceivers, and therefore we don't waste time for this. Therefore, I would say this card is the one that leaves the most possible time, conceptually possible, to the ARM core to answer the 6002 read cycle. You cannot get any better than with this approach. Maybe your application doesn't need it, but if you don't know in front how much time you might need on your ARM core, then I would say this design leaves you most options. And as you see, there's no Pico here. We are going for another development board, which has the benefit of providing all 30 GPIOs. So we have enough GPIOs left to put an SD card there. We are not trying to decode the full address space. This is a classic peripheral card from the A2 perspective in the way that was designed it. That means it has its three spaces, I/O space, slot ROM, expansion ROM. It doesn't try to do any tricks like phantom slots or like these things. It's very straightforward, very classic design from that perspective. This limits, of course, the possibilities. You will not be able to create a graphic card with this hardware. But on the other hand, it's very compatible. For example, all cards that use directly access to the address bus based on the phi clock will have trouble on the 2GS, while this card works in the 2GS just like in every other card, because this is the very design of a card that the 2GS is supposed to be compatible with in the first place. So everything's just work. Within those limits of being a classic peripheral card, we have lots of flexibility, and we will show some of the things you can do with it. These things, I would say, fall into two categories. One is like more emulating something that already exists, and the other thing is trying to create something new, funny. So let's start to explain the first demo. The first demo will be emulating an Apple II Pi hardware. The Apple II Pi started out as in general like connecting a Raspberry Pi, a classic Raspberry Pi, full size, to an Apple II. Doing this via serial I/O, originally using a super serial, then moving forward with a custom ROM for the super serial card, allowing to boot from the super serial card over the serial connection from a virtual disk sitting on the Raspberry Pi. Then the next evolution was to have a custom card, still with a 65 6551, whatever the name is in English for that number, sorry, ACIA. But these are hard to get by right now, at least the ones that work. So there was the idea to replace the ACIA with a virtual one based on an FPGA chip. This card, there were prototypes, it was never realized. There's here of a picture, and this card works with the 4 kilobyte ROM instead of the 2 kilobyte ROM, usually for the super serial card. So this is exactly the card we're going to emulate. And from our perspective, this looks like we have the A2 RetroNet using the original 4K ROM. We have a single USB cable, and we have a Raspberry Pi 2.0 Wi-Fi that uses a slightly modified software, slightly modified Apple II Pi software, because we are using USB instead of serial. So, yeah, have fun.
So this part I'm going to be recorded.
So we are booting, and we see here, waiting for the Raspberry Pi to come up. We are doing a cold start, and the Raspberry Pi is booting a full-size Raspberry OS, including graphical user interface. This takes some time on the first try. Now it has worked. This beep means they are connected. Now the user interface is coming up. I'm not sure that you have all of understanding what the goal of the Apple Pi project is. I'm not trying to explain it in great detail. The idea is that you think of your Apple II now being capable of running Linux. And you do this by redirecting your keyboard, mouse, and mass storage to be available on Linux. If you think that this is a very great idea, or if you think this is basically pretty weird, is a totally different topic. I want to show that it works with this hardware. And what we have done here is we've basically jumped back. So we have now the Apple II keyboard being the input device for Linux. And on the Linux terminal, we are calling back to the Apple and running basic system. And from there, we are accessing Proto successfully. And basically, that's all we wanted to show about this. It's just, yeah, it works as it would be with the original hardware. The original hardware that is not obtainable, and now you can emulate this not existing hardware, and it works. And it works, I would say, nicer because, yeah, of this type of connection. Yeah, I think we are done. Come on. Good thing is we're only trying to do this once. No more HDMI switching. Talking about things that are using the Raspberry Pi, there's another project which is a little bit similar because it too connects the Raspberry Pi to the Apple II, but it's like, I would say, even the opposite of the project that we've seen before. We are going to have a demo with it as well. But in the meantime, while Stefan is preparing the second demo, I will tell you a little bit about a slightly different thing. The Apple II RetroNet card I've shown you has this high-density bus switch on it and has a special whatever thing on it. You might ask, when you think about the nice solder fest for the Apple II VGA, is it possible to do some do-it-yourself thing with R2 RetroNet as well? I would say what you see here comes closest to it. It has replaced the 24-bit bus switch with 3 8-bit bus switches, which are much larger devices, and you can solder them manually if you're a little bit experienced. It's SMD still, not through the hole, but it's manageable to solder these things. This card uses really Pico, therefore there are no GPIO pins left for an SD card. But if you would replace this Pico with this device, it's it has like the same type of soldering things. This breaks out all 30 pins. Therefore, if you would replace a Pico with this one, you would be able to have an SD card as well. So with these type of bus switches and this thing, you can recreate do-it-yourselfable A2 RetroNet hardware. Okay, great. So, but the thing we are here actually showing is not a future thing, but the current thing. The current thing looks like this and has a Raspberry Pi connected via its GPIO. It's a pretty interesting thing because it does not use any FIFO at all, but it uses what I coined a software double handshake dance for every byte. So the Pi and the 6502 need to be like, oh, are you ready to receive? Yes, I am. Okay, then I will give you something. Have you done it? Have you seen it? Yes, I've seen. Okay, then we can move to the next thing, which is, I think, interesting and nice because it's like the Apple II works. You have very little hardware. You have very intelligent software working with this little hardware, and it works. And we are going to emulate this as well. But here, a little bit different because I would think it was strange to have this very complicated handshake. So I modified the lower level of the software a little bit to use a virtual FIFO. And I modified the software running on the Raspberry Pi to use USB instead of GPIO. And yeah, but it works, and it works a little bit faster, of course, and a little nicer. Then we can go. Again, waiting for the Raspberry Pi on a cold start. This time it's faster because we are only booting into Raspberry Pi Lite. There we are. So the ProDOS running here was transferred from the Raspberry Pi over USB to the Apple II, and you can you can just use it as yet another mass storage device, but you can also do some special things on the Raspberry Pi. One of the things is there's a thing that is called just RPi, and you can do any commands on the Raspberry Pi from BASIC. You see here we are just listing a directory. Thanks. And the other thing that we have is you can have a shell open on the Raspberry Pi, and you have some VG100 emulation even. So we are running Midnight Commander pretty successfully and pretty quickly. It's really like usable. You could do everyday work on if you're a Linux guy, you can really use of it. And when we get out of it, things are still there. We are still connected, everything works, and we can then go ahead and use, for example, it to shut down the Raspberry Pi again. So again, very quick demo, not really showing the project, rather showing that the project is correctly emulated on this hardware. Okay, I think I'm now too fast. You had no chance. Okay, we'll need to talk a little bit about this. The next demo is about speeding things up. We will show ADT Pro. For ADT Pro, again, maybe I should point out that the only point where I modified 6502 software was for the thing that we've just shown, where we really replaced that low-level handshake thingy with just accessing a FIFO. Everything else means I'm using 6502 programs as they are. No patching, no whatever. For example, this goes for ADT Pro here. So what we do is we have the ADT Pro client seeing a super serial card, and we have the server on the PC seeing a virtual serial port. And the thing is, again, running over USB. Interesting is that whatever speed you set on both sides, it doesn't matter at all. Speed settings are completely ignored on both sides. And the speed is not limited to anything like 115, 200. The speed is just, what is possible from the 6502. You can imagine like this. The ADT Pro software sits in a tight loop, and looks at its ACIA and sees, oh, when do we have a next character available in the input register, in the receiver register? And then I will grab it. Yeah, you can just see here, every time you ask, there's a character available. You will never touch the ACIA without having the next character available for you because you are too slow. But on the other hand, the 6502 will just regulate the speed because there's no overflow. We are just bringing the characters in exactly the speed it wants to have them because we are, our emulation of the ACIA checks when the 6502 grabs a character and then only brings in the next one and has an end-to-end flow control. Same thing on writing. The 6502 code is looking when is the shift register ready for the new character. Yeah, with this solution, it's always ready to get the next character. So the unmodified software runs faster than ever. Actually, it runs faster than over Ethernet. Yeah, at least on an unaccelerated machine. This is the fastest option you have so far to get ADT Pro running. So we are ready. Great. So we have two 800K images here, and we're moving along. And yeah, this is I think it's running at 2.8 megahertz, right? I guess. Yeah. Mm-hmm. So this is unaccelerated 2GS speed. What I haven't really pointed out so far, what I can do right now is this thing was booted from the mass storage device implemented by the A2 RetroNet. So here we already use the A2 RetroNet both as a mass storage device recognized by the auto start ROM and by Protos, and have it implement a virtual super serial card ACIA. This is not so special at this point because ADT Pro is not interested in anything about the super serial card. It doesn't look at the firmware at all. It just wants to have it ACIA and goes for it. But still, already we have the combination of mass storage and character I/O, same card. And I think it's important, in contrast to about all other solutions, this is not about a phantom slot. The point is, we could not do the phantom slot with the device that we have, but we don't want to, because our belief is that today the problem is not that hardware is expensive and I want to have one piece of hardware do two things. The problem today is that I don't have enough slots. So what does it help me if I have a cool hardware that blocks my slots? I cannot do anything else in the slot because then the phantom slot is already used. Therefore, the priority for us here was to make things happen in one logical slot, not several slots. So here, one slot, slot 7. We are booting from slot 7. We're having no other mass storage device in the machine, and we are still using the same slot. You've seen it in the configuration to transfer data with ADT Pro. Okay. But it doesn't end here. So because it's also about firmware. We have what we call two firmware personalities. We have the mass storage personality and the super serial personality. And they are not mutually exclusive. That's the whole thing about it. And you have already seen a little bit of this. In the mass storage personality, you can, of course, boot from the thing, and you can have Protos recognize the thing. You are not going to have the basic entry points for character I/O, because if, for example, if you do, like in slot 7, a PR image 7 to reboot, you can, of course, not have PR image 7 redirect I/O. You can only have one of those two. But you have the Pascal entry interfaces all the time available. And you have in mass storage and in super serial, you have the smart port entry points available. We'll see about this a little bit later in the demo. And if you go over the super serial personality, you can, of course, not boot or reboot, as I mentioned, but then you have the basic character I/O entry points. So this is really switched, but these two here below are always present. And this is basically I would say, the trick about all this thing. And the other thing is, I have folded all this into the normal address space. There's no functionality of the super serial card lost. It still is full functional super serial card firmware with every aspect it has. It's like, yeah, some tricks. Okay, then let's have a demo of this. We are using the new print shop, and I need to, yeah, and I think we have not thought about the length of this cable. Yeah. Yeah, because I want you to see the output. I have to do this with this notebook, and I need to come over a little bit. Okay. Okay. So what we are doing now is we have again booted the new print shop from our mass storage device. And now we are trying to print from the new print shop. And you see it's configured to use an Apple Super Serial card in slot 7, which is the card slot we just booted from. Okay, and we are ready. And please go ahead and just do the test print, and you can see the data coming through. I've actually left this output for you to see something. No, I don't want to terminate. And here we are. So yeah, works. Okay. Let's close this and go back to the presentation. So what we just saw, to summarize quickly, we started out in mass storage mode. We booted, loaded Protos, and loaded the program. We stayed in mass storage mode. We didn't change it. But nevertheless, we were able to print because the new print shop is one of the many programs which do not rely on the basic entry points of the super serial card. They only rely on the Pascal 1.1 entry points. And those entry points are available in both modes. So you have a mass storage card you can boot from, and nevertheless, you can always print to it through the Pascal entry points without reconfiguration. Okay. Let's have another demo. We will switch back, right? Sorry. Now, we are doing another demo. This time, we will actually switch the firmware personality to show how this looks like and works. Yeah, it was my fault to not hand over the cable early enough, so we will have to wait a moment until this runs. Let me see, is there something to say? Sorry? Yeah, it seems like this. Yeah, it's my fault. Maybe, is there a question at this point?
So the Pascal entry points, can you describe that for me? Why the difference is between them? Okay, having it at 9?
Yeah, for sure. No problem. Basically, you have 3 given standards on how a program that wants to do something like printing can go about it. Besides going directly to the hardware, it has 2 ways to access the firmware. One point would be like if it's in slot 7, you would say, okay, just jump into C700. That would be the classic basic point. But then there are two different types of interfaces that were introduced for the USSC Pascal system, language system. But they are not limited to that. They were just introduced for this. And the Pascal 1.0 entry points are sitting in the expansion ROM right at the start. You initialize it with calling into C800. And there's the newest one, the Pascal 1.1 entry points, and there you have vectors sitting in your slot space, ROM space. I think it's the offsets E, 10, 11, 12, and 13, and these offsets show you where the actual entry points are. It's a little bit like with the PRODOS and SmartPort entry points, like the same idea. Does that answer your question?
It was introduced prior to PRODOS? Or
it's not related to PRODOS at all, because PRODOS is only about mass storage, and here we're talking about character I/O, and PRODOS does not care about character I/O, which is basically cool, because by the time PRODOS boots, it doesn't hurt that there's no character device, because PRODOS doesn't care about it. And later on, we can have a character device, and then PRODOS doesn't care about it anymore, because it has recognized it already and has already put device driver vectors into its device driver table. So it's not necessary anymore that it looks like a mass storage device. Okay, okay, answer? Thank you. So yeah, please go ahead. We have booted into BASIC, and now we are switching from the mass storage personality to the super serial personality by setting the banking. And when we now, I think it's EN image. And when we now say we want to have the input from somewhere else, and we have connected a PuTTY terminal to the USB port, and we can...
I'm talking on my laptop, yeah. So.
Yeah, it's fine. We have connected a PuTTY terminal, and Stefan has just entered CAT on the PuTTY terminal. You can see that it works. So what you can see here is that at the same time, we have super serial card functionality working with the basic entry points, but still PRODOS is connected and working because the PRODOS mass storage vectors are still in place. They are shared between both firmware personalities. Okay, yeah, please.
Question, yeah. So if you were to do a PR number 7 as well, would then everything go to your PuTTY session?
Yes.
Okay.
The point is that with the super serial card and us emulating the super serial card always turns on the bit 7, and therefore the output is not readable, and it would not be nice for a demo, so I just didn't do that, but it would work exactly as expected because it's full super serial card functionality. You could use the small internal terminal emulation of super serial card. Everything is there and works as expected. It's just working basically over USB. It would be like you would have a serial dongle connected to your super serial card, but just faster because you have no place in between with a speed limit. Okay? Yeah. So and it's configured to when you do a control reset, it's setting back to mass storage. So if you now do a PR image 7, it will again reboot. So we have started out in mass storage mode, switched to super serial mode, and switched back to mass storage. Everything is just continuously working as expected. Okay, basically that's what I've written down here. That was the summary of the demo we just had. I think I don't need to read it again. But it does not end here. We have something more. Because think about the super serial card. Basically, a program has two options. The program can either directly call to the ACIA, what we saw before with ADT Pro doing, or it can call into the firmware. Might it be basic Pascal 1.0 or 1.1? And the firmware will then interact with the registers of the ACIA. And then you have the physical output. With A2RetroNet, you can have it differently. You can have it this way. This means we have just implemented a second ECIA. Because they are all virtual, it doesn't really matter. Normally, you would say, if I have a new thing that nobody knows about, who cares? There's no software making use of it. The trick here is to say, but we can easily have the firmware use it. And it's us implementing the firmware. We have hacked the firmware anyhow. So we just hack the firmware a little bit more and make it use the second ECIA. And then the trick is that if a program directly uses ACIA, it ends up with a 1. And this is our USB channel 1. If the program, however, calls into the firmware, it will end up on the second ACIA, and it is another USB channel. So that means basically make sure these are USB channels, not USB cables. It's still one physical cable. The one physical cable transports everything. It's just about virtual devices on the USB. Because with USB, we have the concept of composite devices, and you can have basically many things over one USB wire. And this allows, and the thing is that, what can I do with this? Programs tend to use this path for printing because it's so nice and simple, and they tend to use this path for modem control because the firmware is not really capable of controlling modem well and doing speed and not losing characters on receiving, while printing is only sending. It's simple. So usually firmware I/O for printing, direct I/O for modem control, and this is something we can nicely make use of. So we have the next, I think, final demo where we do character I/O in both ways. And I need, again, to connect it here because I want to show you what's coming out. Sorry? Yeah, right. What I'm doing here, I haven't really explained it before, is starting a virtual printer that is listening on some COM port, which is my virtual serial interface that was created by the A2RetroNet card. And then here I'm starting the TCPI TSR, maybe you know it. It's a program especially created for retro computing that is like a virtual modem. You connect to your virtual modem via serial interface, but it connects to the outside world via TCP/IP instead of modem. So you call, for example, into Telnet BBSs or stuff like this. We have not modified neither TCP ESR, nor have we modified in any way the virtual retro printer. This is just the way you can download it and run it. No modification, neither on the Apple II side, nor any software that I'm running here on Windows. It's just all stock software. Okay.
I did not power up the clock.
Sorry?
I didn't have the right cable for the... Somehow we didn't bring the right cable to power up.
I think we had it here. It's lying here. This is the one to be used. So because we don't have a good internet connection here, and because I personally think it's a nice scenario, we are not going to call into some BBS system, but we are going to log on to the Linux running here over TCP/IP, in this case over Wi-Fi. So you can see here, looks strange. You have your ProTerm configuration, and you say that you have an Apple Super Serial card in slot 7, And you say you have a Pascal 1.1 printer driver, also in slot 7. No problem. ProTerm doesn't think this is strange. It's just funny. It's nice. So we've booted from slot 7. We have a Super Serial card in slot 7, and we have a Pascal 1.1 printer interface on slot 7. Now we are connecting to our target via the TCPi ESR program running on the notebook. So this is going over USB to my notebook, and my notebook is running this TCP SRR. You see this is running on COM port 8. So we have two different COM ports. One, in my case here it's 8, is the channel for the direct SIA, and the 9, COM port 9, we are having here. Yep, 9, is for the printing over the firmware.
Are you connected to the... Not finding us.
I think I am. Let me see. It says I'm connected to Cisco 2550 70.
I'm not finding this. I can't ping it either.
Let's give just a little time to see if we can fix it. Otherwise, we have to go without. Ping 192, 168, 100, 135, ja? 135? Yeah, it's not.
I can try pinging only.
I think we need to maybe continue, so I will, let's see. Sorry?
It's not coming up.
You have the SD card too, right? Yeah, for sure. That was the last one we used. Okay, so for reasons beyond my control, this has nothing to do with the actual software we want to show. It's about the environment, because as you saw, I couldn't even ping the device I want to log into from my PC. So for some reason, our network is not working the way it was working yesterday evening. So, so this is now not a summary, but rather a replacement of the demo. We have it configured this way, and you would have been able to see that we log on to the Raspberry Pi, again having the midnight commander visible and stuff like this. And if we then said we want to have something printed from A24 Pro, then it would show up. Maybe we can just print a file instead, so we can see that printing works independently from the modem stuff. It's on file, you can say just file, print file, and then you have the welcome below, the lowest, or below, it's a short thing. Yeah, just file, print, welcome, and where print. Okay, whatever. I think we're running out of time now. Okay, so in case you are interested to seeing this live, we have some days left. I'm happy to show this at another time. So now for some additional information. Basically, here it worked. So you see with this, yes, the printout that we just created. I don't know why it didn't why I didn't see it. So in general, this worked. Okay, let me continue quickly. Okay, the whole picture is A2RetroNet is a split solution. The actual A2RetroNet board is to be seen as a front end from the Apple II perspective. The Apple II sees the A2RetroNet with its port, its firmware, and whatever. But beside the local mass storage implemented by the SD card, everything else requires a backend, something that is connected to the USB cord. And these things connected provide Wi-Fi, for example, which is great because, as we have heard already, doing Wi-Fi from within an Apple II GS just doesn't work. But if you have a nice short USB cable, and this cable is the only cable that you need, then you can have your Wi-Fi just outside of the thing. And for the Apple II Plus and E, you can nicely put it on the side inside the housing. These additional devices can support mass storage, virtual modem, virtual printer, virtual real-time clock, other stuff. Just to visualize, A2RetroNet connected to a PC, what you've seen here. A2RetroNet connected to Raspberry Pi 0 to Wi-Fi, as you've seen here. You can as well imagine to connect it to an ESP32S3, because the S3 is a variant of the ESP32 that has native USB support. And you can even think of connecting it to a Raspberry Pi Pico Wi-Fi. I personally don't think this is interesting because the other things do more and are not more expensive. But if someone thinks this is exactly what he needs, it's absolutely possible to do it. It's really nothing that would not work. So if you say, it's so nice, but I hate that it doesn't have a Wi-Fi antenna, this Raspberry Pi Pico Wi-Fi is even cheaper than any antenna you can have. It's much more usable, and you have basically the same effect that you have here, the PCB antenna outside, or you have it where you want. I think we are sort of at the end. I would like to cover this. I think one or the other of you might have asked, yeah, virtual printer, virtual modem, remote mass storage things, this sounds pretty much like FujiNet. So what is the perspective here? The interesting thing is we are not competing with FujiNet. Rather, this is complementing each other. Look at it from this perspective. The FujiNet is a nice backend. It has many functionalities already built in out of the box. You don't need to configure and get this stuff together. It's there. And it's running on many hardware variants. That might be surprising to you. Of course, natively, FujiNet comes from running on the ESP32. But there's also FujiNet PC. This runs as a user space process in, for example, Linux or Windows. So you can run it on your notebook, or you can run it as user space on your Raspberry Pi 0. So basically everything I showed can nicely run FujiNet, and you can have the functionality. So looking at it from the perspective of FujiNet, you see that A2RetroNet brings native modem and printer interfaces. This is what exactly currently is missing. If you use FujiNet and connect it via the smart port to, for example, whatever, then of course there's printer and modem functionality. It's over smart port character I/O devices, but no Apple II software never knows about this and will use it. You have to create new software, you have to patch software. But as we've seen right now, A2RetroNet exactly delivers this, the interfaces that every existing Apple II software expects to see for printing and modem control. So it's basically exactly the missing puzzle piece in the FujiNet picture that A2RetroNet brings to the table. And it's faster because the USB connection is just faster than the old-fashioned classic smart port C-bus. And I think that was it. I think there's no time for Q&A, right? Or
You can take a few minutes, we have a break.
okay. So, do I take some questions? Okay. So, yeah, these questions. So.
Although, can you repeat the question?
Yeah, I will try to. I'm sorry that I didn't before.
Question about like your review of the A2VGA part that we saw here.
Yeah.
So comparing to the other option, the alternative option, which acts as a soft card, do you think this A2 VGA that we soldered yesterday can potentially be a soft card?
A soft card? Sorry. You were asking about the Apple II VGA card and about its potential to be used as what? Sorry.
As a soft card, like
CPM soft card.
yes,
so-
like Z80, like the other.
No, the one that you soldered is certainly not doing this because it's not able to do anything with ROM. It's just not able to. It's not capable to react on the request of the Apple II to read a ROM, neither the slot ROM nor the expansion ROM.
Although I think you mentioned that it's bi-directional, it can send data both ways.
Yeah, I think the soft card. Maybe I'm wrong. The CPM soft card. Yeah.
I'm sorry, just looking here. The VGA that he's talking about is a different project.
I
Well,
understand.
yeah, the one that you soldered last night was stripped down and had features removed to make it
Yeah.
simpler.
Yeah, but sorry, I think maybe he's even right because the soft card, in contrast to the Appli card, does not have any ROM. So maybe the soft card could be possible. But I think this is leading pretty much far. Maybe we can discuss this somewhere else. Maybe I would rather like to take some more questions. Yeah. Okay.
You had several slides that showed the Raspberry Pi 02W. Is there anything that requires two or the 0W work?
Okay. So the question is, I've shown a Raspberry Pi 02 Wi-Fi. Why this exactly? The point is that it's nice and fast. I think it's the ideal device for this purpose. It has a low enough memory current consumption. It's small and it's fast enough to be fun. You can as well do it with a Raspberry Pi Zero not 2 Wi-Fi. You're just waiting instead of 7 seconds on the cold boot, you're waiting maybe 20 seconds or 30 seconds. It's just not so much fun, but it's absolutely working. And in general, nothing I have shown is in any way limited to the Raspberry Pi. That's a great thing. We are talking about USB. Everything single Linux single board computer that has a working USB port and has support for the CDC, ACM class devices and mass storage class devices can be used. It's just the same. And sorry, I would like to add, we have not shown at all that we have access from the Windows machine to the SD card. So the SD card on the A2RATONet can be seen from the Windows machine just like a USB thumb drive. So if you want to have another image put there to play with it, you don't need to remove the SD card, but you can just copy the files over and be done. Sorry for not showing this, I just forgot about it. It's an interesting feature, but I just forgot about it. So now the next question, please. Yeah.
Is Glenn planning to make the cards?
Yeah.
And is there a sort of a rough timeline?
Yes.
Thanks for this question. It's about, is this going to be really produced or is this just a fun project? It's certainly going to produce. This is basically just a pre-production prototype. This is certainly going to be a product. And it's, to answer your questions, maybe, it's going to be not more expensive than a Usernet 2. Maybe same price, maybe even a little bit cheaper, but certainly not more expensive than a Usernet 2. It's supposed to be, it's not clear when it will be exactly available, but we will have very soon a limited beta program. The limited beta program will work like this. You pay the full price of the final product. You receive the current prototype. You are committed to provide feedback on your experience with the prototype. And in return to your feedback, you will receive the final product as soon as it is available without additional charge. Basically, for your effort on participating in the program, you will have at the end 2 cards for the same price, the prototype and the final product. This is how this is going to work.
Yes.
Two questions, just to wrap my mind around what we saw there with the
ProTerm running.
Yeah.
Did you have to flip into that super serial card
No.
personality
No.
beforehand, or
No, not at all.
Okay.
So maybe just, yeah. So the question is, did I have to switch to the super serial card mode in order to run ProTerm? Not again. The ProTerm is yet another example of a program that doesn't really care about the ID bytes of a super serial card. You just tell it, okay, in slot whatever, you will find a Pascal 1.1 character interface, go ahead and use it. If I would have said, do this in slot 6 or 5 or 4, it would just go there and would have undefined behavior. I'm always surprised how little programs actually test things. You just tell them, do it, and they do it, which is great for us. Yeah, the testing, which is just great for us, because otherwise you would have to patch out some recognition routine because you cannot be everything at the same point. On the other hand, maybe if you have a program that really relies on having the basic entry points and therefore the super serial personality, imagine you could have a very minimalistic add-init program that just does this switching after Protos has booted and is fine. So you can say, as soon as I've booted and my add-init program has run, I'm sitting there with a fully functional super serial card while still having Protos accessing my thing. The only thing is that I cannot say PR image whatever to reboot. And therefore, the idea that maybe people would like the idea when they press Control Reset, maybe that puts it back. But as soon as we have a configuration program, which is of course necessary, missing today, this configuration program will allow to enable or disable the idea of having Control Reset, bringing you always back to the mass storage personality or not.
Yeah, it seems like there's a lot of, I guess, kind of opportunity to expand on the ideas here. Any thought of open sourcing any of this?
Yeah, thanks for asking this. The only reason why it's not open sourced right now is that it would be maybe embarrassing for me to show you all the ugly hacks that are in there. But no later than when the product is final, and therefore the code is final, both the hardware design and all the firmware will be open sourced. So by the time this is a product to be sold, it's going to be an open source product in any respect. Thank you.
Yeah, thanks.
Any thoughts about 2C, 2C plus?
Okay, the question is about the 2C plus, 2C. I think I would say on the 2C, which has its C-bus smart card interface, I would think that the FujiNet is pretty much a natural device on that thing. Because, yeah, I think it's basically, that's the answer. I think we are really thinking of complementing, enriching the FujiNet experience put off. And for the 2C, I think what FujiNet does is a natural fit already. So there's basically no need and no additional benefit of doing more. That's at least our current perspective. So hopefully that's okay.
Yeah, quick question. I noticed that you have an SD card on. Are you running that in SPI mode? Are you running that in SDIO mode?
This is plain stupid SPI mode, 1-bit SPI mode. Because
You're using FAT32 as the...
yeah, sorry for not repeating the question. The SD card on the device is running in 1-bit SPI mode, and it's having an XFAT. We're using the FAT-FS library, so you can look at the FAT-FS project site, what all is supported, and we support everything that's there. It's a lot. You can even have large file names and things like this, and a lot of interesting
I'm just curious, because I ran into some performance problems in that library. That's why.
So we are pretty happy. We have done very, very early benchmarks, and we are close to the CFFA 3000 running on a USB stick. We're not really there, but we are close to it. And we had to time. Maybe we can come up later on. We can, for example, see how nicely Total Replay runs from the card. And the performance is, of course, not compatible with what we've seen before lunch, but I think it's appropriate and what you usually expect from a typical mass storage device on the Apple II. Yeah, sorry. Thank you very much. If you have more questions. Let me start with saying that I really enjoyed giving the session on site. And I deliberately tried to not make this, let's say, a marketing session for the A2 RetroNet. But as long as there are no other questions here, let me talk a little bit about the A2 RetroNet. It's one of the cards that have been created in the recent past that works with a Raspberry Pi Pico. Also here, we are not really using the actual board, but rather the RP2040 that is on this board. The reason is primarily because the Raspberry Pi Pico board has 4 GPIO pins, which are not available for the developer, but they are used internally on the board. And as the RP2040 is sort of short on GPIOs, we decided to rather use the bare chip in order to have all GPIOs available. The board that I had with me in Kansas City and that I demoed together with Stefan Wessels is the latest prototype. There will be more prototypes, and there will be a limited beta program. And everybody who is participating in this beta program will have to pay the final price and will receive a prototype and is asked to provide feedback on his experience with the prototype. And as soon as there's the final version of the product, he will receive additionally the final product without additional cost. So everybody participating in the beta program will basically come out with 2 devices, a prototype and a final device for the price of the final device. Regarding the price of the final device, it is supposed to be either identical to the Ethernet 2 or less than the Ethernet 2. And what else can I say? On site, I've been also asked about open source policies around this product. The current idea is that as soon as the final product is made available, both the firmware and the schematics and the design files will be open sourced. So this is supposed to be in how's it called? A commercial open source product. Okay. Great. These are the things that I felt I could want to say, and now I'm really open for any maybe potential questions.
Yeah, so Jesse in the Discord asked about how many devices are they? So many of your images have kind of a peripheral card attached to a cable to something that's outside, right? And you tried attaching a couple of different things to that card. So what are which part is the device?
Okay, great. Yeah, thank you. Great question. So when I'm talking about the A2 RetroNet, I'm talking about the card that goes into the Apple II. And you can either use the card on its own, or you can connect things to the card. If you use the card on its own, you have a rather nice mass storage device that is based on the SD card that is placed on the card. You have the usual approach of having an FAT32 file system on that card and having files with disk images on it that you can then use to mount as virtual hard disks. Additionally, you can connect, for example, your PC to the card, maybe only temporarily, and then you have 2 features. One would be that you can download from your PC to the SD card additional files, additional disk image files, because the card looks to a PC like a thumb drive. And additionally, you could, for example, run ADT Pro on your PC and use the card as a replacement for a super serial card. It's just much faster than a super serial card. The next option would be that you instead connect to the card something that you rather intend to keep connected to the card. This could be, for example, Raspberry Pi 02 Wi-Fi, or maybe an ESP32S3. And then you can run some specific software on that augments the capabilities of the Arto RetroNet. So it's a rather flexible modular idea. And you can either use it on its own or connect additional things to have additional functionality. Maybe especially interesting might be that you can run a specific variant of FujiNet, which is supposed to be implemented primarily by me, that augments the capabilities of the Arto RetroNet. Okay, so I see now that there are, I think, some questions in Discord as far as I see. One of the questions is, can PC and Apple run at the same time? I guess this refers to access to the SD card. Yes, actually, really, you can, if, for example, while the Apple II runs, you can add a file, or if you, for example, would, let's say, replace an already existing disk image with another one, then maybe your very next cut command on Protos 8 would already refer to the new one. Basically, it's just like removing and replacing a floppy disk in your drive. And the question, when is this a good idea? And when you maybe should not replace the floppy disk in the drive, it's up to you. And here it's the same, it's up to you when you modify the content of your SD card while the Apple II is running. It's more or less up to you when you think this is a good idea or when this might lead to any type of issue.
Yeah, I see that Josh asks in the chat or in the Discord about collisions. There's a number of storage options now, and was wondering about whether you had any idea about whether A2 RetroNet would collide with Ultimate Drive if and other new things or old things.
Yeah. Okay. I can of course not really talk about the Ultimate Drive. The Ultimate Drive is, from what I understand, a rather, let's say, aggressive device, using a lot of DMA, using the ready line. On the other hand, the A2 RetroNet is an extremely, let's say, defensive device. It does not use any specific things at all. It just uses the very classic pins for a device. So it does not do DMA. It does not provide a phantoms part in another slot or does any other fancy thing. It's a very, let's say, from the perspective of the Apple II, I would say the Arto RetroNet is a very simple, very simple and classic device. Therefore, I would say it's as compatible to anything else as it gets. But of course, I cannot say anything about compatibility with any other specific device, especially if it's one like Ultimate Drive. Okay, I hope that answers this question.
Yeah, still interesting to know, I guess, what I suppose what the strategy is, what the philosophy is. Chris asked whether, was it difficult to do did you have to do anything special to make sure that the Pico boots and runs quickly enough while the Apple II starts?
Interestingly, the boot time aren't a problem. I have the Pico running in slot 7 because that's where the boot scan starts. So the time is the shortest. And at least with an Apple II GS running at 2.8 megahertz, I could not see any problem. I could even have some delays in the RPi Pico boot and could never see a problem. Maybe a highly accelerated Apple II could run into trouble, but I don't have such a device, and therefore I cannot test it. But at least with some rather stock slotted Apple II, there aren't problems. And running quickly enough is, of course, a challenge. As I mentioned in my talk, let's say answering quickly enough on a 6502 read cycle is always a challenge for any microcontroller. But with the help of the programmable I/O, we have here a solution that works at a really very attractive price point.